Hi everybody, this is Mrs. Ellsworth, and what we're going to be looking at now is on the back page of our notes, the acceleration formula. Okay, and go ahead and write down this formula right here, but I don't know if this one's very helpful for us. If they give you the change in velocity, which my problems don't, mine break it down even more to where I'll give you the final velocity. Maybe you need to write that down. The final velocity is the ending velocity, and the initial velocity, which is the beginning of the situation. Okay, and then the time, of course, is during the time period. That's why they got the change in. And so this equals the average acceleration. Okay, so let's go and manipulate this for a few different types of formulas for where you're solving for final velocity, initial velocity, or else time. So if we're solving for time, we've got the final velocity minus the initial velocity again, the end minus the beginning, and that's all over the acceleration. Okay, and then we can manipulate it again for the final velocity, and that would equal the initial velocity plus the acceleration times time. Now, if your thing starts from rest, this will be 0. So that would be pretty nifty. It would just be final velocity equals acceleration times time. There we go. Okay, so what if we're solving for the initial velocity? Then that's the final velocity minus the acceleration times time. Okay, so like if you're looking at units, and you'll have to write these down. So like the velocities could be meters per second, then that'd be over seconds. So it'd be meters per second over seconds, or else meters per second squared. And we'll talk more about that again for the acceleration unit. So it would be meters per second, time would be seconds, and then this would be meters per second, or meters per second squared. Okay, it could also be kilometers per hour over hours. Then our unit for acceleration would be kilometers per hour, or kilometers per hour squared. Okay, so let's look at this first situation. At the start of a race, a toy car increases its speed from 0 meters per second, that's our initial velocity, to 5 meters per second, that's our final velocity, that's where it's ending up at, as the clock runs for 2 seconds, which is our time. I like to go and write down, my variables underneath each number that's up in there, but sometimes you're asked, you should be writing your givens down here, so it makes it a whole lot easier to solve for it. It wants the acceleration, so it's going to be an A equals formula out of the one that we had. Okay, so then the final velocity is going to be the 5 meters per second minus the 0 meters per second. And this is all over the 2-second time period. And so there it is there. And then we get for an answer 2.5 meters per second, or like I was talking about, meters per second squared. Okay. Okay, moving on to the next one. Oh, I guess we're going to talk about some formulas first. Okay, so here's one of those formulas that we had. And then so when we start going and combining some of these formulas, I used to go through the whole type of ways that we come up with these different formulas, but now I don't. I just have students write these down, okay? And we're not going to go through how we get these formulas from these formulas being inserted to the other formulas. Okay, so moving forward on that, if you start out with 0, okay, like our last problem, it started from 0, then this right here would all be 0 because your initial velocity would be 0. Just like if you were starting from 0, oopsie, then, oh gee, I lost it. Oh, right here. So if you're starting from 0 here, then you would then you'd be able to ignore this portion of it too if your problem was solving from 0. Okay, so we're going to go right here next. And in this problem, let's go ahead and read it. Okay, a jet taking off from an aircraft carrier goes from 0 meters per second to 113.64 meters per second, okay, about 250 miles per hour. It does that all in 30 seconds. So of course we want to go and follow the meters per second, not the 250 miles per hour, because we've got seconds here, and it's a huge hint also because it's in metric. Anyway, it wants us to find the meters per second squared, the acceleration that, so we've got to use this unit here and this one here to be able to follow through for that. Okay, so the acceleration equals the final velocity over the initial velocity, and now we'll go substitute in the values. So the final velocity is going to be the 113.64 meters per second, and we'll subtract the 0 meters per second. Okay, and then that's all over the time period, which is going to be 30 seconds. When you do that, you get 3.788 meters per second squared. And you might be thinking like, well, Mrs. Ellsworth, you're not following sig figs. Well, I wasn't going to do that this video, just so that we get a handle on the math part of it, and then we'll worry about sig figs next time. Okay, so we've got the acceleration figured out. So it accelerates 3.788 meters per second faster every second. So it's taking off. So now if this is a constant acceleration, we're saying if this acceleration is constant, then how much time does it take for the jet to reach twice its speed? And you might think, well, it's going to be twice the time on it. But let's go through and make sure. So the final velocity is going to be twice the speed, which is 227.28 meters per second. We've got that same acceleration. Okay, and so let's figure out the time. So that's the final velocity minus the initial velocity all over the acceleration. We figured this formula out on the previous slide. Okay, and so we've got 227.28 meters per second minus 0, and then we're going to put that over our new acceleration we just figured out, and we're going to get out of that, we're going to get our time to equal 60 seconds. So that did work out right. Okay, so now they want to know, with that same new speed that we're talking about, and how long would it take for the what distance would it take for it to reach that speed? Okay, so we're going to do distance divided, hold on. This thing is starting from rest, so we get to use this nice smaller formula of, let me get these all written up here, sorry. Okay, so we get to use this nice smaller formula of 1/2 equals AT squared. We can take off that VI, or the initial velocity, times the time. And so when we do that, we can go ahead and substitute in our new acceleration that we figured out in the first problem. Okay, and then we can do that time that we just talked about. Okay, and so that's 60 seconds. And we got to square that, of course. I sometimes forget that, so I punch that in my calculator first. Anyway, so when we do that, we should get 6,818.4 meters, okay, because that's the distance that it took. You can cancel out these seconds here, and you can get that. Okay, I see I have an error here. This should be seconds squared for the acceleration, and this seconds here be squared too, so you just have meters left over. Okay, so just looking at this information here, okay, hold on, I got an error. I see I neglected to answer something back at the top of the page here. When is the acceleration negative or positive? So we need to be thinking about the direction of it, and we're still going to follow the number line and the XY axis here. So here we know that this direction on the XY axis is always going to be positive. This one's going to be negative. Okay, and when you're going up, that's a positive value, and when you're going down, that's a negative value. So sometimes these things are kind of like a double. Okay, and double negatives always means it's positive, right? So we got to look at it. So we got a car that's going up a ramp. Okay, it's going up, so it's going to be positive. Okay, and it's stopping at the top. So as it goes up, it's slowing down. Okay, so as it slows down, that acceleration is negative. But it's going up, which is positive, but it's slowing down as it goes up. So this is going to be deceleration. You know that that vehicle is slowing down as it goes up the ramp without any extra energy. So that will be a negative acceleration. Okay, the cart going down the ramp. Well, think about it. Going down, that direction is negative, but now it's going down and it is going to be gaining in speed, so it's positive, so that's still negative acceleration. And that one's kind of a, not a gotcha, but, well, maybe. Okay, so a falling object is going down in the negative direction too, okay, and it's accelerating, so that will be a negative acceleration also. Okay, oops, gave a hint away on that bottom one. Okay, stopping for a stop sign, it is not telling us any kind of direction on here, so we do some assumption. Okay, so what is the direction on this? We don't know. So we're going to assume that we're starting here at the origin and that we're going in the positive direction. Okay, so it's going to be a positive direction. Okay, so it is stopping for a stop sign, so it's slowing down. So that still will be negative acceleration or else decelerating. Okay, so now if you're going to be passing a car at the beginning of the pass, you're stepping on it. Okay, and it didn't give the direction here just like this one either, so we're just going to assume it's in the positive direction. Okay, and so it's going to be a positive acceleration in this case right here. Okay, after passing the car, okay, then you slow back down to 55 miles an hour, and so that right there, you're slowing down after you pass them, right, because it's after you pass them. So that's going to be decelerating because we don't know the direction, so whenever we don't know the direction, we're going to assume that our writer of the problem wants us to know that it is in the positive direction. Okay, so I hope that helped explain some of those, because a couple of these in the beginning might have been a little bit of a gotcha. Okay, so now your notes are completely completed for the whole packet, and I will see you when I see you.